So apart from theory, let me just start that you need to mount this drive. So if you click on this cell, there is a pop out in which it asks for permission from our connect to Google Drive. It will ask permission from our account. If you do this, you just have to click at allow. So after a while, you should be able to locate the drive folder in notebook itself. So I think you will be able to locate this drive folder in your directory. If you click on this in Colab, there will be drive, and if you go into this, you should just change the base directory wherever you added the shortcut. Wherever you added the shortcut of workshop data, there should be a path. So for me, the path is this. So whoever like have different version of location in like shortcut, you can just change the base path so that there should not be any error going further. If you added in Google Colab notebook, so just go there and click here, right click, there will be path to copy, and just paste here. So this should be your base directory. Whoever have added the shortcut in Colab notebook folder. Whoever added the workshop data folder in this Colab notebook, you just need to change this variable which is called the base directory. If anyone have added the shortcut in different folder, so accordingly he can locate using this drive, and just click right click and copy path, and there should be an option to just paste here, so that you can change the base directory and you will be able to run all the cells. So I think I have given you enough time, so I will now discuss that what I am going to tell you about. So let me summarize whatever we have discussed today. So initially Abhimanyu have told you about that how can you code cleanly, what are the data types. He have told that X array have certain type of advantage, and later Mannath have introduced us to the data types in geophysics. So seismic data have a certain standard type which is called the Seismic-well, and the last file have a standard type. The well data curves are located in a standard file which is called the last file. So in the fourth notebook we have loaded them and created into X array and exported them. So whoever was not able to do this, we have already created a folder in which we have already loaded those X arrays. So now I will tell you the next path in how we can use that well data in seismic data in machine learning. So as we know that last data have a domain in depth, so it is measured along a depth wherever we drill, we measure the depth at which we have measured the property like sonic curves and other things. And the seismic data have a vertical domain in time. It could be two-way time when we do the acquisition. So seismic data have a z-axis of time. So if we want to locate that well data into our seismic data, then we need a relationship of that depth to the time of seismic. Otherwise, we will not be able to locate where our well is, and if we are not able to locate, then we will not be able to find that what kind of seismic data we have acquired along that well path. So apart from the time depth relationship, we need a deviation survey. The deviation survey have a path in terms of what are the x location and y location along the depth. So we need to merge these kind of files. There is a time depth file and there is a deviation survey file. If we do the merger, then we should get a relationship in which we should have one column as a depth and other column as x and y and a time axis. So this is the basic thing, and if we are able to locate those x, y, and t, then we will see that how a well look in 3D. So we can see in background how a seismic look and how a well look, and it should introduce you to the topic that how we can use the seismic data to do the inversion using the machine learning. So I think I have told you to change the base directory wherever your data folder is. So if you run this directory, it will change our base directory. And next, these are some library which we are going to use to load the data. And I think these are the similar library we have used: Pydantic, Segway-Sark, and Lasio. Even though we do not require it, but because there is a similarity in the between notebooks, so we have not changed that. So for this project we have 4 wells. So if you can see the name of those 4 wells, so something called 59, 11-1A and 1A and something like this 11T2. So for your convenience, we have merged the deviation survey and time depth file into a CSV file. So if you go to your directory, you will be able to locate this XYT folder, in which for each of the four wells we have this kind of relationship, in which one column is the depth axis and the second column is the time axis. As I told, the last file is in the depth and the seismic file is in time. So we need a relationship between depth and time, so that we can locate vertically that how where exactly well is, and in terms of that 2D location, we need x and y along the time and depth, so that we will be able to find exact path of that well into the seismic. So if you if you read this list of well names and assign that our well, we will do the analysis for well number 1, which is the 11-1A. And if we load this file of dfxyt, so you can see that we are able to read that CSV, and you can see that relationship between depth, time, x and y. So what we are going to ensure, like you were able to get this data frame loaded. Okay, so we will go ahead. So now I will discuss that how we can do the seismic well tie, and we can using the Python. So what are the things required to do the estimation of seismic well tie? And basic idea is that using the well logs, we create a synthetic which is similar to the seismic. So we compare that synthetic with the seismic, and we are able to find if we are able to find a good correlation between the synthetic along the well and the seismic along the well, then we are convinced that the well is exactly located in that path. And so For seismic well type preparation, as I told that we will need, I have written a function in which we will we will do the input of well loaded in X array, and we will convert that into data frame. And the second file required is the XYT file, in which we have the relationship between depth, time, and X and Y. Now these, you can see these three code are simple thing. We are trying to get the time axis along the last file which we have loaded using this some kind of interpolation because we have the depth the XYT file in which we have the relationship between depth and the time. So for the new depth, so there is a simple library called NumPy interpolation. If you go into, if you click on this, you can read the syntax what exactly it do, and you can like it is a 1D interpolation kind of a thing. So for the new depths we require these time axis, X axis and Y axis. And the second things I have written in my code is that we have loaded some kind of curve in our X array. So DT syntax is for the compressible slowness. So here I am changing the unit from to the SI unit, so that our all the logs we are loading, it should be in SI unit. So say it should be in like if we are following one unit type, then we will convert all the log into SI unit type. So to convert the DT by from US by feet to meter, we will do like division of this factor. So it is simple thing in which there is a relationship between a feet and a meter. And obviously you can do that by how to do the gram by cc conversion to kilogram by meter cube in terms of density. So we will multiply by 1000, and using the compressible slowness we will be able to calculate the velocity. Its unit should be meter by per second. So this is the factor, and we know that acoustic impedance is a multiplication of velocity and the density. So it is simple thing that we have multiplied those two columns, and we have got new columns, and we have also written that unit in terms of kilogram by meter square into second. So by this way we are able to create new logs and change the unit. And so here the function is written to convert X array into data frame. So it is like we in earlier path, in earlier notebook, Mannat has shown us that we can use that last file and create the X array. And for the convenience of you to see the data, like you will be able to see the data in data frame very easily. So we will convert that X array into data frame. It's just for convenience. It is not a good approach, but for the convenience of us, we can like just convert into data frame. So this is a simple thing. We have assigned our well name to be the first well in the list, which was 11.1a, and this is the directory of wherever we loaded. So our loaded folder is in the base directory folder called loaded. So if you run this, so I will now run this up in the cell number this.
So as you run that, so how many of you are aware of well to seismic tie? Why do we do well to seismic ties? When we already have seismic data, why create a synthetic seismic? Right, so that is one reason. Right. Any more reasons? So one is time to depth. The other one, the other answer I had was well logs represent some kind of ground truth. Seismic also represents another version of the ground truth, but well logs have a direct property measurement embedded in it, right? Why else would we do? Somebody said resolution. So what about resolution? Right. I think I can follow your thought process. It's that the log data has very high resolution. The seismic data has limited resolution. Somehow you need to use log data perhaps to increase seismic resolution. That's okay. That's a whole different story. But the well to seismic that we are doing here, right? So we are not going to do any resolution enhancement. But why do we do it, right? So you work with this question, right? So that's right. So in like in interpretation workflows, so well is point information and seismic is it's lateral information, and in well you can identify the horizons, right? So when you do the synthetic seismogram creation with well, you can identify the important horizons and you can track them laterally, right? So that's another reason. Any more? Any other point? Okay, so again, yeah. So that's again the resolution point, right? So yeah, that is an important question that is being addressed, but yeah, right? So yeah, so as you do the exercise, I would like you to think about these aspects, right? So why do it in the first place? And what happens if you mistie well and seismic? Does it matter? Right? So
Okay. Let me summarize whatever we have done. I told you about this function we have written so that we can use those X array loaded and convert, find a new columns, the time column, the X column and Y column, and change the unit into SI so that we can use those for our seismic well tie. And even though we have created the time file, the time column, X column and Y column, we can see that our data frame is uniformly sampled along a depth axis. You can see there is a uniformity in between difference. You can see it is a 0.1, 0.1, 0.1. But time axis is not uniformly sampled. And if we want to create a time series out of it, we need to resample that data into time domain and at a uniform sample. So I have written a function to convert that depth domain data into time domain, and we can resample by like simple. I have not written a complex thing. So so we can get the x new, in which we will try to find that in earlier data frame what were our highest TWT point and minimum T point, and we will assign a sample rate, that at which sampling rate we want to change that time axis, so that we will get a data frame in which the time axis should be uniformly sampled. So here for the simplicity I have given our time axis should be at 0.2 millisecond, and I have also assigned a list of columns which I want to convert from depth domain to time domain. So first is the depth, and these are the unit we have changed, and we also told that we have added some column in terms of time, in terms of x, and in terms of y. And by basically applying this function, you will find a new data frame along which there will be a time axis, and you can see that time axis is uniformly sampled. So so we need to convert a depth domain to time domain if we want to compute reflectivity and convolve with a particular wavelet. And the next function is because we have loaded the seismic, and we know that each trace what is the exact x of that seismic and what is the exact y of that seismic, and we also know that what is the path of x and y along the well path. So if we just simply plot them together, and we can see that in the whole 3D our well path is along this direction. So well path start from something like here and it goes, so this is the direction. We can see it is not vertical, it is deviated along, it will pass through many traces. So there is a in 3D direction there should be a in 3D there should be a path along which well we have drilled. So it is not only vertical path but a deviated path in terms of x, y, and we can see. Now this is the simple seismic file we have loaded. So this is the, you can see the first trace has a x location of this and y location of this, and what are the number associated with it. You can see the first trace mean that inline number something this and inline number something this, and this is the first trace in our data. It could be at the boundary here, here or something. You can try to do plotting at yourself, so I will not do it here. And as I told, we know the path of well along the seismic, and now we will load that X array that Mannat have told us how to do that. So this is the simple X array, and if we just I just put a thing that how an X array look like, you can see that what are their coordinates. There should be some time axis, and there is an inline axis, and there is a x line axis, and every inline and cross line combination have a unique combination of x and y, and there is some data variable in which all 3D data. So you can see the shape, that how, like what is the exactly shape of seismic. You can see along the time axis we have the number of sample around 1126 and x line and inline. If you want to go into detail that what is written in header, you can also, you will be able to find the sampling rate. You can also find that domain is the time, and how the measurement we have done in those unit are x and y. And if we go here, you can see what is the sampling rate along the z dimension, which is our time. So here we are able to see that our time axis uniformly sampled around 4 milliseconds. And this is like if you are even if you have seen seismic data in commercial software, first thing we do is to look at the header they have given. So there is some kind of information that what exactly is the what are the range of x line and inline, and what is the range of x and y, and some other information, and what are their byte location at P. And during the acquisition, if they will have written something which could be useful to us if we want to go into detail. So for us, we will utilize this 3D data and do the seismic extraction and do the seismic well tie. We will create some synthetic along the well path, and we will do the correlation with the seismic, and then we will judge that whether the time depth relationship we have, how much quality of that data is. If we are not satisfied with the data in terms of x, y and time relationship, there are ways to change it, and we should have certain constraint that how much amount of we can change, but that is not the scope of today. So we have created this x, y, t relationship in commercial software. If you go into the data folder, there are some deviation survey and TD files. So these are not the CSV file, but if you like just download it and read it, that how exactly we are able to find x, y and t relationship. So you can go into detail and do this merger by yourself, because you will be able to see that how exactly raw data look, and in future if you want to use, then you can do the merger yourself. So by going to the next code, as I told, we know the XY path, XYT path along the seismic. So next thing what we can do is, if there is a way we can extract the seismic data. So seismic data could be velocity, seismic data could be amplitude, and if we know the XYT path, and we can write an algorithm to just extract along the well path. But here for the simplicity, what I have done is like whatever our XY path is, we will just use a mean location in between. So mean location of that XY path could be in between, like we will consider that well is vertical. So that what is the nearest seismic trace in it is, so I have written a code for that. If you go to that the nearest seismic trace find, so we will take an input of something called df size header. So during the loading of seismic file, we have created this CSV in which there is a relationship between x, y, inline and cross line. And let me just show that what exactly this file contains. So there is some trace axis there is a CDP x-axis, CDP y-axis, inline and crossline axis. So we know that at which stage what exactly is the x and y, and we also know that each stage what is the amplitude of that seismic trace along the time domain. So here for the simplicity I have just taken the mean and find a unique combination of x and y, and by using the library of SciPy, in which we can just assign them the number of point we want to find, that what is the nearest point of that whole seismic 3D along the well path, then we can here just get the combination of that particular combination of inline and cross line. We will slice the X array, as Abhimanyu have told, that we can use the coordinate of inline and X line and just do this here, and then along, as we have added the time axis along the depth, we will also add the seismic along the well path. It is not exactly along the well path, but due to the you can just write a code for it. Obviously I have written a code for it. I can just show you that how can you do that. For each path in well data, you can just take that point and just try to find that what are the nearest 4 or 5 traces. So based upon the bilinear interpolation, you can just find exact location of what should be the amplitude, and by this way you will be able to find a better code. I have just assumed that well is vertical, but that is just an assumption, as we know that well is not vertical. So we will just do the seismic extraction, and we will be able to find a seismic along the well path. So to summarize here, like whatever we have done from the previous thing, we loaded the X array in depth domain, we have added the time domain, we have added the X location, we have added the Y location, and we have converted the units to the SI system. And then we wanted that our time axis should be uniformly sampled. So we just assign that our dt should be something like this, and we have got the data frame. Now we have also got the seismic along the well path. Not along the well path, but with the assumption that seismic, that deviation, there is no deviation, but well is vertical, and it is vertical at the mean point of that deviation path. As I told, you can write a better code at your home or wherever work you do. So, and I also told the philosophy that how can you do that. So we have this data frame, we have the seismic, and we have the this acoustic impedance. So for seismic synthetic tie, what we do is we will compute the reflectivity. So there is a formula of reflectivity. Can anyone tell me that what is the formula of reflectivity? That how we calculate the reflectivity from acoustic impedance? Obviously. So so I have written a code for that resampling, that RC computation, which call the reflectivity, and here it is the reflectivity. So when we have the reflectivity, we have the seismic. So first approach is to use a wavelet and convolve with the reflectivity, so that we can get closer to the seismic resolution, not at the well resolution, as we have already agreed that well resolution is very high compared to the seismic. So we will need a wavelet convolution with the reflectivity, so that we can estimate the proxy of seismic from the well, which we call the synthetic seismogram. So here I have written a code for the recur computation. You can go into detail what exactly a recur wavelet is. So it looks something like this. There is a peak frequency, and there is some so here it is written, it is zero phase wavelet, a second derivative of Gaussian function, and there is complex thing, but you can just go, if you want to go into detail, you can. So this is the most commonly used wavelet in seismic analysis. So we just use this kind of wavelet where we apply that what should be peak frequency, what should be in length in terms of time, and what should be the sampling rate of it, and if we want to do a phase change, then we can just do the Hilbert transform and just do the phase shifting kind of a thing. So after calculation of this, I have written a code to visualize this wavelet. So you can look at this. So if you go to this code, as I told, Ricker take input of peak frequency and what should be its length and what should be its phase. So here I have just estimated, I have just guessed that what should be my peak frequency and what should be it. And when we convert into data frame, and so this is the part where we estimate the proxy of seismic from the well data. So we will use the reflection coefficient and we will do the convolution with the wavelet amplitude. So W is the wavelet amplitude, and if we do the convolution, we get the new column which we call the synthetic. So this is our proxy, and how we judge that how we judge that well tie is good. So as I told, the synthetic is a proxy of seismic from the well data. We will calculate the correlation. So here we are able to see that correlation is around 0.68. So like we can just change this peak frequency from 20 hertz. Let us see that okay, so it is 0.65. Maybe we can just go higher, 50 hertz. Like how exactly? So like we are able to see that when we change the peak frequency, the correlation is decreasing, because well data have a high resolution and seismic data does not contain that kind of information. So we can just estimate the wavelet. This is a simple code I have written for the workshop, but there is also other approaches in which we can optimally extract the wavelet by utilizing of the reflection data and seismic data. So these are called the Roy-White wavelets, and there are some other method also in which you can just optimize that at what kind of wavelet my correlation will be at highest point. So just for the guess, like I have used the 50 hertz peak frequency wavelet, and when I did the convolution and calculated the synthetic, and we got the correlation of around 0.1. How do we visualize? Like this is the simple code to visualize that wavelet. So if you click on this, you will see some kind of wavelet which have a peak frequency around 50 hertz, and it will decrease as we go further. So here next I have written code that how we can plot this synthetic, seismic, and those well logs of acoustic impedance and all other things. So if we just do the 1D plotting, we can see that this is our synthetic and this is our seismic. So what conclusion we can find? Can anyone tell us that how this seismic data look and how this synthetic data look? Any observation from you? Okay. As I told, that frequency content is too high for this correlation. If you overlay this, you will be see that there are certain minor variation which we cannot see in the seismic. So let me just see in terms of 2D that how does it look. So I have written code, so I will not explain that how I written code. So there is a simple thing, as we have calculated the data frame in which we have the seismic, we have the synthetic, and we have all the things. Now we want to plot and see that how exactly well looks in a 2D. So I have created a function in which we can just change the direction, whether it is in line and cross line. If you see that this is our seismic and this is the wave, this is the synthetic we have created. Obviously, this look something this like this because the sampling rate of seismic is very sparse. We use the reflectivity of 0.2 millisecond, and the seismic data is around 4 millisecond. So when we do the resampling, this amplitude get distorted. But even you can see that the seismic data does not have that kind of information. So here comes the problem statement. The AI and deep learning is venturing into field that they claim that they can learn a complex relationship and they can just predict anything which we call the black box. So there is a good problem statement here, whether we can utilize this kind of information which has a high resolution. But the problem statement is that we have the limited number of well location, because we cannot drill at every location. It is costly and it is not efficient. So it is a good problem statement in deep learning that we have the low resolution seismic and we have the high resolution well data. if by developing some models and so that we can predict like this kind of high resolution, and we will be able to propagate this kind of resolution into whole 3D seismic. Imagine you can see that this kind of resolution into seismic, and if you want to locate any geological anomaly, it could be your reservoir sand, or it could be anything in gamma ray. If you see that our depth resolution is around 5 meter, but if we go into seismic, we cannot find any signature. So if we overlay, then we can find a good problem statement in deep learning. You can utilize this seismic data, which we have extracted along the well path. You can utilize the well data, and you can create a deep learning model in which you will take an input of seismic which has a low resolution. The model will try to learn a complex relationship between that seismic of low resolution to the well log of high resolution. And if you are able to do this, then you will be able to get a seismic of well log resolution. So this is the exact problem, exactly one of the product we solved at Resalytics. So if you go into our website, there would be some comparison in terms of what we do. We utilize this kind of well data, but well data is very scarce. As I told, well data is limited location, seismic data is very abundant. So you can just think that what we can do and how we can enhance our spectrum or the information content we have. If you just go there, this is the input seismic we take, and in between these are the 3 logs we have. These are the synthetic exactly we have calculated, and when we tie, you can see that there is a distortion of amplitude and there is a lateral discontinuity. We cannot exactly see it high resolution. How does it look? But as I told, we have the well data at high resolution. We can use that seismic data to predict this kind of seismic, and we can go even further, but that will not look good us too. So this was the basic problem statement. As I told, you can plot in second direction, which is the x line. So I want you to play with this wavelet, and you can just change the well name in this cell. So there is an exercise for you. So I have loaded the first well in the list. You can just go to this cell, the initial cell number 7, cell number 8. I have just loaded do the TD analysis for first well. I think there is an exercise for you to go choose any well. It could be first, second, or third, and play with the frequency, play with the phase. Let me know that whether you are able to get a good tie or bad tie, or what are your conclusion. So here is a break for you, like for 5 minutes you can try, or if you have any question in between you can ask me. So this is the base directory wherever you added the shortcut. I think many people were able to get this data frame. So there is an exercise for you to change the well, play with the wavelet, play with the frequency, peak frequency, play with the phase, and whether you are able to do anything further or what are your conclusion. So you can just let me know. It's not horizontal, it's a 2D space. As I told, it is you can go into complexity where you can plot along the well path. You can also extract along the well path, which we in this example I just estimated that our well exact is located at the mean of that deviation path. So this was the assumption for this workshop. For you, this is a good problem statement to write an algorithm where you can extract along the seismic path and where you can plot that x line and inline along the well path. So there will be good exercise for you to learn. So here I told change the well, change the peak frequency, and whether you are able to get that seismic synthetic correlation for other well or not. So I will wait for 2 minutes. If you have any question in this part. Okay. Anyone can think of any other problem statement they can come up with when they have the seismic data and they have well data. What are the things they can do? Like anyone want to just get into discussion, they can just rise up, like stand up and let me know. So it's all working fine. Anyone who have loaded the other well and changed the peak frequency and phases and was able to get good correlation? Go here, just change the well name. It could be third number, it could be fourth number. If you code along, then it would be more interesting. Otherwise, it's just a lecture. I don't want it to be boring. So that I will show you that how we can do for other wells. Let me just load the last well. So what should be the index for it? 3. So what now I loaded the well name at the third of list, and as we change the well name, there should be change in the dfxyt we loaded, and I think I will run all along by just clicking this, not clicking this. Okay. So here I am just guessing. I am not changing any frequency, any phase, just see, like I want to see that what exactly happening in that well. Like we will see another plot in terms of seismic well tie. It's running, so it will not take much time, but you will be able to get the plotting part of it. So it's running. So we see that correlation is very poor. So what we can do? We can just decrease the frequency. As I told, seismic is very low resolution. So I'm just changing the frequency and trying to find a correlation that should be up to our expectation. If we got a correlation around 0.5 or 0.4, it is also low. So what we can do, we can maybe play with the phase, or just have a look that how 2.26 correlation look like. If we do the 1D plotting, then we will be able to see that what is the relationship between the seismic and the synthetic we have estimated. You will be able to see that. So these kind of things are there. And at the bottom, it is not matching with the synthetic because we have assumed that well is vertical, but it is not vertical. If you extract the seismic along the well path and do the seismic well tie, it would be around 0.5 or 0.6. So it is a good exercise for you to think about an algorithm where you have the XYT path and where you have the data along the XYT path. So now I will go to an example that where we can utilize the machine learning part. That is the focus of our workshop. But here comes the 5 o'clock and we are able to reach here. So anyway, to just introduce you to the problem statement we have. So here it is written that we will try to predict the sonic logs. So sonic logs are compressible slowness and shear sonic. And why are we trying to predict it? Because in terms of acquisition, when we do the drilling, these kind of logs sometimes are missing, and because they are they required a high amount of cost to do the measurement, and there are some other logs which we can easily acquire without requiring of any other sensor. So here is a good problem statement in machine learning. By utilizing the other logs which are easily available, whether you can predict the sonic logs which are more useful in terms of estimation of the synthetic seismic trace. So this would be good exercise for us, and it would give us the better overview that how machine learning can play a role in this. So as I told that it is like basic overview that we have the 4 wells and these are the names, and we have already loaded them. We have converted into X array, and so this is another type of log plot function we have written. So Mannath have showed you the another version. So it is a simple thing to get another version of that log plot. So we just load. We will use that 4 wells. So the problem statement it is that we can utilize the 3 wells and just trying to estimate the sonic of these wells. We exactly know the answer, but even without providing the training data, whether we can get a model which can learn a complex relationship between other logs, like where we have mentioned that those are easy to acquire logs. It could be density, gamma ray, resistivity, caliber, and all these kind of things. We will utilize these kind of log to predict the DT and DTS. So as I told, DT is compressible slowness and DTS is shear slowness. So it is just a plot to, like, we are just overlooking the data, that what exactly contains in the data. So we have loaded the X array. So as we know that below this depth we do not have any data, actually above this depth, because it is plotted reversely. So we can just discard the data because we will not have any other well to predict this kind of logs. So we will just constrain in vertically that whatever logs we have, we utilize this kind of data to predict the sonic part of it. So here comes the data preparation. So in machine learning, the large amount of time we spend is to data cleaning and to prepare the data prior to feeding into model, because feeding into model and predicting model is not very complex thing. Obviously it is a complex thing if you go into detail of how that networks work, how these kind of different machine learning work. But the major part of any data scientist, machine learning engineer goes into cleaning the data, overlooking the data, and like do the finishing prior to getting into the model. So there is a quiz for you, like how many of you are aware from the machine learning algorithm. So any algorithm you have worked with, or you know the basic thing. So you can raise your hand that you know you have worked with any machine learning algorithm. No one? I think someone. So I will just try. There is a quiz for you. So there is a quiz that what is overfitting. So by the name of, you can like guess some kind of a thing that what could be an overfitting. So you can just stand up and speak loudly. Okay, I think he answered correctly, but he told us that in overfitting we have some kind of training data. We can fit a model to predict a good quality result on that training data, but if we utilize that model to predict those data which we have not injected, like say test data, where the model haven't seen that kind of data. If our model is not able to do that, then what is the purpose of machine learning? So we need to avoid this kind of overfitting. So overfitting is in basic terms, we are not, the model is not robust enough to predict on unseen data. So like there are ways to avoid it. So can anyone answer that how we can avoid the overfitting? Okay, another? Okay. Okay. Any other from this side? How can you avoid the overfitting? So I have written some answers. So I have also plotted some kind of a thing. So these things. So I think you are saying something about cross validation. Okay. So I think you have come again. Okay, like there are various approach. I will discuss some of it. So like these, there are three scenarios. There are two different data set, two different classes, but we are trying to get a model which can separate them. So you can see first model is the underfitting model. So what is an underfitting? We are like we have created a model, but it sometimes can fail. It sometimes can tell us that the green classes it sometimes can tell that red data is of green classes, but they are not of green classes, but they exactly are the red classes. So it is not also our goal. We do not want our model to be underfit. And another model is the overfitting model. You can see there is a now nice complex boundary between the classes. You can see it is separating the training data very well. But if you use this kind of model into unseen data, then it can also fail. So this is not our goal. We just want this kind of model which is balanced, which should not be underfit, which should not be overfit. It should be balanced, so that we can get a model in which we can even predict the that test data or unseen data. That is the goal, that you have some kind of data, you try to feed into network, it will learn some patterns, and it will utilize that learning to predict those kind of variation in unseen data. So here it is written the answer. We can hold out means we can separate the part of training data for the validation. And in terms of cross validation, there is a basic thing in cross validation, because we can let's say we have the 100 number of samples. We can give him a factor that you just cross validate by the factor of 5. So it will divide the whole 100 samples into 5 folds, each have a 20, and it will train the model 5 times, and it will try to predict by giving the input of 4 slots. It will try to predict the 5th slot. So it will in this way we can see that different part of data set will go into validation in each new training, and if we are able to get a good model in even that scenario, then we can reduce the overfitting, and we can do the feature selection. Let's say we have the some variable, but target variable, but we have some kind of input. We have lot many input which do not have any relationship with the output. But if we have large amount of data, it could happen that machine learning can learn a pattern which is not useful for him to go to the output part. So in terms of that, we can discard some features which are not useful for our prediction. If you are aware with the neural network, we can remove some layers, or we can reduce the number of neurons. We will discuss that what a neural network look like. And there is some dropout, we will drop some neurons, and there is early stopping. Early stopping is a criteria in which we are trying to pass the data n number of times, and we define that if consecutively 5 times, if we are not able to reduce the loss of our output, then we can just hold, because model is not learning any new thing, it's just overfitting on the training data, and we will not have any robust model in terms of output that will predict on the unseen data. So these are the approaches. You can go into detail at your workplace, so that you will have a better idea that what an overfitting and underfitting and how we can avoid in different scenarios. So this is a simple thing I have written, that I will drop the values where we do not have the exact answer of sonic wells, sonic clocks, and it is just a transformation in terms of resistivity. So resistivity we have converted into a log domain, and the de-spiking part I think Mannak also spoke. that in terms of despiking, there are certain outlier along the window path. We will assign him a window path that choose a 25 meter or 5 meter window length and try to find a sample that is outlier or that is a spike that exactly do not follow the rest of the sample. So in this way we can get rid of the outlier which are not which will not help us to train the model better. So here I have just loaded, I have just applied similar part. We are not repeating. We have written a function. So for each of the 4 wells, it will do the data preparation part. And in the end, I have just selected that fourth well, the fourth well, which is my test well. I will utilize first 3 well to build a model to predict the sonic logs on the 4th well. So you can also run this code, and you will be able to see that how the first well after despiking look like. So these are the wells I have, and prior to going into any modeling, we just have to look at the data, that what is the relationship between different variable, what is the relationship of gamma with the sonic, what is the relationship of resistive with the sonic, and what is the relationship of resistive with the gamma ray. So this is a simple code in Seaborn, the Seaborn library. You just need to assign a syntax of pair plot. You will assign a data frame. There should be data frame should look like this, in which we have different kind of columns, and it will just plot that what are the cross plot in between different kind of logs, and at the diagonal we can see the distribution of its log. So it tells us that how this log are distributed in terms of their x values. You can see there are 2 different classes, some are having high density, some are having low density. So it is a good method prior to going into any machine learning model to look at the data, that what are our variables which we are going to predict our target. So in terms of after doing that, we can also do another approach in which diagonal in here is the diagonal of. So it is a distribution along the x-axis would be values and how these samples are distributed. So you can see that last path here DTS is written, in the x-axis the values are written 100, 20 and 30. So it is telling us that the majority of DTS values are between 100 to 200. There could be some values which are above 200. So in terms of we can see the distribution, it is a simple thing to look at the data. So it will give us the cross plot in between different curve, and it will give us the data distribution of curve we have. So I think I have plotted here, and I will just do again. And the next part I will do is I will try to find a correlation, that how our different log are linearly related with the other logs. So it is also a good exercise prior to feeding into any network. If we find any log which or any data, any column which we think it is not having any effect on the output thing, then we can just discard. As I told, there are ways to reduce the overfitting, and one of the method is to feature selection. So it just give us an idea that if the 2 features are linearly related or not. If even in the input variable, if 2 are very collinearly related, then we can discard one of them, because they will not do any new information in terms of, because if those 2 are very linearly related, then we can see that their variation will be also same. So in this way we can do the analysis and do some feature selection part of it. But always a feature selection is a trial and error. We just select some and we try to find their weightage, that how one feature is exactly having how much weightage they have in terms of output we are receiving. And the next part, prior into feeding into any neural network or any network in belief, let's say we have the logs of gamma ray. Their absolute value could be different. We have the resistivity, we have applied the log, their absolute value could be different. DT could be from different, and all things could have a different absolute value. But in terms of machine learning, when we are trying to find a complex relationship, those absolute value does not matter. What matter is the variation along that path or what variation they are having. So we are not, in the normalization, we are not changing their variation, we are just synchronizing their scale, so that every data comes in a one scale. It could be 0 to 1. There are different methods that how we can do the normalization. One normalization could be that so here a formula is written. So can anyone tell that what could be the range of this, if I put an x, what could be the range of this x scaled? So any guess, anyone have? 0 to 1. So if we have the x is equal to x mean, then the x scale could be 0, and if we have the x mean, x as x mean, then we will have the x is equal to 1. So this is the simplest method that we can use to rescale all the absolute value into a similar scale into 0 to 1, and we can utilize that kind of information and to learn the complex relationship between our output variable and the input variable. So another way could be we can use our mean or standard deviation. So we can calculate their mean, and we can subtract the mean and divide by the standard deviation. So this is also another method to do the normalization. So here I have just used the min max scaler, where different logs would be scaled into 0 to 1, so that we can fit a model and try to. So there are some libraries to do that. So here I have imported a library and I have created a scalar, and when I fit the transform, what I am doing here it is that the training, I am calculating the x min or x max of the training data, because we do not know anything beyond the training data. So whatever in this formula, whatever x min or x max we are using, it should come from the training data, and similar formula should be applied on the test data, even if they have a different x min and x y. So in this way we will have a synchronization between the test data and training data, and by this I have also written the function which we will take this kind of input, and I will do the scaling part of it. So here already written for the different wells, I am just plotting, I am just using this kind of function in which different log, different data frame will go there, and their variable name, and based upon that I think we can because the well df is the concatenated file of all the four. So based upon the well name we can differentiate that which data frame is of which wells. So here comes the part of modeling. So if you have any question up to this part, you can just ask me. So all okay till this part? So let me summarize. We have loaded, we have seen at the data, we have seen the distribution, we have seen the correlation in between, we have scaled the data. Now we are ready, because we have the some input variable and some target variable in terms of sonic. So idea is to get a model so which can learn a relationship between the input variable and the output variable on the training data set, and it should be able to predict on the unseen data set. Then we will have a confidence in terms of our model that our model is learning something which and trying to predict on the data which we have not given him. So here are some written, these are the simple idea written here. So you can do, this is the simplest example I am giving here. Obviously this is not the end of machine learning. There are certain different kind of networks are there. There are some RNN, there are some CNNs, there are some neural network, there are some shallow learning models. You will need to go into detail of each of the network, that how they learn this complex relationship. All idea of modeling is to learn this complex relationship which we cannot do using the normal regression or normal linear regression. So this is the basic idea. So here it is a diagram. So has anyone seen this kind of diagram prior to this? So can you guess what it is? So anyone just want to explain me that that what these nodes are, what is the hidden layer and what is the output layer? Anyone have an idea? So let me explain. The simplest neural network explanation I can give it is that we have some input variables which I told there are different logs, gamma ray could be, density could be, resistivity could be. and we define this kind of a architecture in which at the input layer we will take the input of those other logs, and there will be some neurons. These the black markers are the neurons, and these or you can see that any neurons you see, that it is every other in the previous layer, every other neurons having a connection with it. So it is called the feed forward neural network. So in which we are passing the information from input direction to output direction, in which let's say these are the first of the layer of first layer, in which it will try to find some pattern in terms of input. Some nodes will learn some kind of feature, it will have some kind of weightage, let's say, and second input will learn this different feature from the input, and it will have a different weightage. So at each of the node in next point, those there should be weightage sum. So if you go to the next layer, so this is the calculation look like. So at each of the node there from the previous layer, each node we will do the calculation of weight of each of the node, and what are their feature they will learn in terms of x1, x2 and xm. So and we can do the summation, and we can do addition of some bias. Bias could be, you can understand in terms of an intercept kind of a thing. And later at each neurons, have you understood that we are giving them some kind of input, and we are telling them that this kind of output should become here. So if we pass in first time, let's say in first iteration we give this input, then these neurons will automatically adjust the weight in between, and they will try to find a meaningful pattern, in complex pattern in between, and they will estimate some kind of output. Let's say in first iteration the output is very different from the whatever we are trying to do. So basic idea is that it will calculate the loss in terms of, we can assign a loss function. It could be mean square error, it could be mean absolute error, it could be root mean square error, it could be anything in terms of what your loss function look like. So there are different kind of loss functions based upon the advantages and disadvantages, and in terms of classification and regression there are different kind of loss functions. So idea here it is that we will calculate the loss, and these neurons will tell the previous layers that whatever you were trying to get me through the answer, it was not correct. So these neurons will try to adjust their weight and in terms of feature. They will in next iteration they will try to change their weight and whatever they learn, so that we can get closer to the answer. So our losses are getting back propagated, our information is going in this direction. So this is the basic explanation and simplest explanation of a neural network, where we have created many layers. Some input layers are there, some output layers are there, and some between hidden layer. So we can play with it in terms of how many neurons we want, how many layers we want, and as I also told that there is something called dropout. In dropout, what we are doing in each of the iteration, we can just drop one of this feature. So if we drop one of this feature, then it could also happen that whatever it was trying to learn, if this neuron has a very high amount of weightage and a very complex pattern, because it could also happen that this neuron is only depending upon this. But if we drop this, then these neurons will adjust the weight in between, so that weight is uniformly distributed, and any particular feature is not only is our affecting our output. So this is a basic explanation, and as I told, we do this some kind of calculation at each node, in which in previous all the nodes from the previous input will have some kind of weightage in terms of what they learn, and we will do the summation and we will add the bias. And here comes something called the activation function. So anyone have any idea that what an activation function is? Anyone heard? Okay, so this is the right answer. As I told, we are trying to find a complex relationship, and which we were not able to do with the linear regression. So we have something called the activation function, in which we are just transforming the input calculation we do by passing to this function. So it will look like something look like this. So there are some formulas here. So these there are I have given the 4 references in terms of activation function. First is the ReLU, and second is the tan H and sigmoid. Here you can see the formula. Based upon the formula, anyone can guess that what could be the what it is doing in terms of ReLU. So here it is written that the maximum of 0 or x. So what it is doing is that any in terms of the calculation we are doing, any output having a value less than 0, we will replace it with the 0. So you can see the formula, maximum of 0 or x. So if any value is having less than 0, then we will introduce you the nonlinearity and we will replace that value with the 0. So this is the simplest way to do the nonlinear part of it, and there are other functions in terms of what is the tan H and sigmoid and leaky ReLU. So leaky ReLU is from the name you can see there is a modification in the ReLU in which we are not replacing the negative value with the 0, but we are just we have written here a formula that based upon certain factor we can multiply, and it will have something lesser slope than the positive values, and something called the tan H. In tan H there is some complex formula here written here. So value of here it is always in between -1 to 1. If we want our feature to transform any value from -1 to 1 and do this kind of things, then we can do with tan H, and there is a sigmoid, and in sigmoid the values range between 0 to 1. I will show you that. So here comes an question that what is an optimizer. So anyone have any idea? Obviously we can use, and in the output layer if we want only positive value we can use the sigmoid function. The output layer will always be between 0 to 1. I think we can use, ReLU is the most commonly used. This is the basic. First we try with the ReLU. If we are not able to do this, then obviously whatever you are saying that our output is having a value between negative or positive, then we can use the ReLU or not. But we are like saying in terms of the calculation at the node point. We are not going into the absolute value of prediction at the weightage, in terms of the next time how this weight will be different from the previous iteration. So based upon that we are doing introducing this kind of activation function. So ReLU is the most commonly used, and the tan H and sigmoid is also there, but they have their disadvantage and advantage in terms of what our application are. So we start with the ReLU. If we are not able to get there, then we use other. So here comes the question, what is an optimizer? Anyone have any idea? So what is an objective function? Okay, I think she got the answer that in optimizer from the name we can guess that what we are doing. We are just in the neural network, we are trying that our output should be closer to the truth values, because we are giving some training data. We will calculate some kind of estimation. If our output y is not exactly that we are trying to feed, then it will calculate the loss, and each iteration it will try to minimize this loss function. So here comes look like this. So in first iteration our loss value could be very high. In next iteration our loss value could be lower, and in terms of step you can see that if we are converging at the minima, and each of the iterations we are calculating a very less amount of gradient descent. So it is called gradient descent. We are like descending from the high loss to the low loss, and we are it is like in Adam optimizer we can reduce our when we go to the minima we can reduce the learning rate, because if we come here and if you calculate the loss, and then we can go here, but that is not our objective. We have to go to the minima whatever we have. So there are many types of optimizer. You can go at home and read. So basic idea is we have to go to the minima of our loss. So our model parameters should be optimized, our weight should be optimized. so that we are able to get a good model and we can predict even at the test data set. So I think I have, so this is the thing. So this is the neural network I have written. So here comes the sequential part. Sequential is, as I told, we have a feed forward neural network. One layer will provide the input to other layer, and it will, there should be input layer, there is some hidden layer, and there is a output layer, and output layer have a two outputs, because we are trying to predict both things, dt and dts simultaneously. And here I have applied the sigmoid function. Can anyone guess why I have applied here? Finding the, but here we are doing the regression. As I told that we have also done the normalization on the y part, and we have scaled all the logs in between 0 to 1. We want our y values to always be between 0 to 1. So as I told, sigma function do the input and try to extract any value between 0 to 1. So then whatever output we are getting, we can do the unscaling part of it, and we can get the absolute value from the whatever scaling we have used earlier. So here it is, I am saying that when we are doing the training, save my model at this path. So my model is saving in this path, and here comes the optimizer. As I told, the optimizer function is to minimize the loss and get at the minimum loss function. So our model parameter should be optimized, our weight should be optimized to get the minimum loss, and it should be able to predict even at the data which we have not seen. And we have also, for the prior to training, we have some given that save this model. And when the monitor, so monitor function, we are trying to say that when you are iterating, going to first iteration to next iteration, when you save the model, you just monitor that whether we are able to reduce the validation loss or not. And the mode here it is minimum, because we want our validation loss to be minimum. And you can go into detail in function that it is trying to try to save the model which are giving the lowest validation loss. And here comes the overfitting. How we avoid the overfitting? It is the early stopping, because here we are giving that if you monitor that our validation loss is not reducing continuously for 10 epoch, and minimum delta is that we are giving him threshold that if you are not able to improve the validation loss for 10 consecutive model, then you can just stop, and do the training part should be stopped here, and we will go into prediction. So in the model fitting, we have given some training data. So training data from the 3 wells. So what is the x? X are those gamma rays, density, resistivity, and y is the dt and dts. And here comes the batch size. Batch size is that in calculation of loss function, how many number of samples we are giving at a point of time. And epochs we have given 50, but also we have given him the criteria that how you can just avoid and stop whenever you require. So this is the basic part. I think I have to run the modeling. I don't know how many amount of time. Let's wait for it. How we will see that how it learn and what are the syntax its output, what are the output area. So we have given him the criteria. If you are not able to improve the validation loss for 10 epochs, you just stop there, and I will use your model to do the prediction. So it may take some time, may not be many, maybe 1 minute, 2 minutes. Based upon the amount of data we have, based upon the complexity data we have, time will vary, because we have only 3 wells, and 3 wells are not very large amount of data. But complex neural network require a very large amount of data to learn those kind of feature. But I am just giving an example, and so that you have created an interest in deep learning. You can look at the different kind of models they have, and it should be a good starting point from you that this is how we can apply the deep learning part for the geophysics, and try to do the prediction of those logs which we were not able to measure. So this is an idea. So here comes, you can see in kernel that what it is outputting. It's saying the validation loss improved from this to this. In first iteration it also improved. In fourth iteration it also improved, and you can also see that in each iterations how this validation loss is varying, how this mean square error is varying, and how this loss is varying. So here loss and mean square error are same because we have given them that use loss minimum square error as mean square error as our loss function, and in terms of matrix we can also use another use like it could be mean absolute error. So it will give us the output of mean absolute error at each of the epoch. We can just say that we can use the R square in regression. So we can look at the quality, and we can also plot this kind of variation along the epoch path. So and here if you are not observed that there is something called learning rate. So learning rate, simplest explanation of learning rate is how much amount of step you are taking. If learning rate is too high, then it could also happen that we are trying to change the weightage by a very large number, and we are trying to go very faster to the loss, and that was the not ideal part of it, because we should have an optimum learning rate. And also if we have very low learning rate, it could also happen that we are just not decreasing the validation loss even if we are giving so many outputs. So it should be optimum, and usually it is around 0.001, but you can also vary and see that whether we have improved or not. So I think you should wait for 2 minutes. Let us see that how model learns and what kind of prediction we have. Any other question apart from whatever I explained? So can you can anyone explain me what is a neural network? Because I have just told you what is a neural network. So whatever have you understood, can just explain me that I have understood this part of neural network. Anyone? Either I am teaching too like good or too bad, maybe. So here we are not constrained by the depth, but we are giving them, we can reshuffle this data. It does not depend upon the depth. It only depend upon the time in when we are using those network like RNN, which we depend upon the time axis, because we are remembering the previous data to predict the next data. But here we are not remembering the time axis data. Here this resample data, we have some deleted some samples because we are just trying to fit a basic model. In terms of complexity, you can use LSTM also, you can use the RNN part, and those they are not very complex, but for the introduction I have just given you simple example that how can you build a model and try to do prediction. One meter for output where are written. No, in terms of calculation, we are calculating the mean square error. So in each iteration, it will select the 5 sample. It will use all the sample, but at a time, how many samples I am giving to calculate. So let's say we have the many number of samples, but for when I calculating, we will not give the whole data at a point of time. We will give the 5. In next part, I will give the 5. So based upon the mean of that, I can calculate the loss and I can do these kind of things. So as our model is learning, I can just show you the result. I did the training prior, and I can just show you that what kind of result look like, and you can see when you obviously you can use it.
There are two ways to do this. You could create your training data in small image patches and create X-ray out of those image patches, or you can write a data loader which has the logic, because essentially if you want to create patches from images, right, that's what your challenge is. So how do you do that with numpty? You write a data loader, right, which is going to extract patches from those images. So you can write a similar loader which has some logic. Okay, take this patch, this patch, this patch from the image, maybe 28 by 28 or whatever the image patch size is. So you can write a data loader that reads data from an X-ray rather than a numpty. Should be fairly straightforward. Because X-ray is nothing, it has the numpty array underneath. So you should be able to dot data of that and just get the patches out as if it was a numpty array. Nothing new there.
Here we can see that validation loss is not improving since 21. So I hope like it's early stop, because over the next 10 epoch it was not able to learn any new thing in terms of validation loss. So we just stopped the learning. Now we will just plot that how these losses look like along the epoch. And we will compare the loss of validation and training. Hopefully we get a better picture. So just plotting. So in history we can save anything we given in terms of metrics. We can save the absolute error, we can save the R square error, we can save the root mean square error. So whatever requirement we have, we can just use the Keras library. So Keras is the simplest library because it is built upon TensorFlow and other we can change the backend also, but for the beginner this is the basic library you can work with. And here I have written the code that you can see that like up to something like here 20 something, the minimum loss is something like here. So it is not learning any new thing and loss is increasing after. So we will not utilize this kind of logs, this kind of model to do the prediction where we have converged at the minima. Then we can choose this kind of model to do the prediction on the test well, which we have kept out for our prediction. So we will see that how much, like what kind of result we are getting. Obviously it would be a good exercise for you to look at the alternative model. It could be shallow learning model in terms of gradient boosting, it could be means neighbor or other many algorithms are there. You can see in terms of cross plot that how much amount of R square number we are getting. So R square is a measurement of regression, that how closer we are to the output we have. So if it is saying that our R square factor is around 0.974, then we can see that we were able to predict the sonic part of DTC at this rate. This is the accuracy matrix, and this is another accuracy. We can see that DTS is not at par with this, but in terms of 0.85, it is also a good number to begin with. And obviously I have told you can just try to improve this model so that you can get even better number than this. You can use any complex, you can use any alternative model, or you can just do the better parameterization in terms of you can just play with the number of neurons we have, play with the non-linearity we are giving, or you can just change the optimizer also, and you can change the loss function also. So it is for good. I think we have to go into detail in batch library. I am not at a moment prepared to answer that, but obviously you can look into detail of what batch size do. You can just click here in model fit and just say that what batch size exactly doing and how you can go on the view source. It will open a new .training.py file and what exactly batch size is doing and whether I have just you can look into detail. Obviously, I will try to find the exact answer. Okay. So in terms of prediction, as we were discussing that this kind of metrics we are giving, like the R square factor of 0.94 and 0.84. In terms of if we see along the depth that this much at this much accuracy, if we plot the truth part behind, and the orange part is our prediction, you can see that we were able to do the prediction even if we do not have the answer of DT and DTC. So this is a good program to begin, good model to begin with. Obviously, there is always scope for improvement. You can get even better number than this. And I think this was the end of discussion. I think if you want to summarize me, I just first we discussed about the how we can do the seismic well tie. In seismic well tie, we converted the depth domain to type domain data. We have extracted the seismic. We have chosen a wavelet, and we have then done the estimation of synthetic. And in terms of by overlaying on 2D and 1D data, we have seen that it was having a very good correlation with the seismic. Then I also introduced you to the problem statement where you can use the seismic data of low resolution to predict the data of high resolution. And then at the end, I have shown you one application of machine learning where you can predict the missing log by utilizing of other logs. So this was the summary, and we were able to get a good number, and I will hope that some of you go home and try a new model and approach me and tell me that I was able to get a good number. So it would be a good discussion with you.